Hi, and welcome back. We are talking about equilibrium systems or equilibria systems, and we're going to apply that concept to acids and bases. Now, strong acids and bases ionize 100%. We use that single arrow. Weak acids and bases ionize less than 100%. So when they ionize less than 100%, we use a double arrow, and we form an equilibrium between the reactants and the products. In other words, we reach a state in which the rate forward is equal to the rate reverse. And we seem to have a steady state situation, at least on the visible order of magnitude. All right. Now, what we're going to use are the symbols Ka for the equilibrium constant for an acid. Notice that's a capital K. And Kb for that of the base. Now, you have these values. If the question doesn't ask you for them, it's expected for the homework. You can look these up on the tables that are given to you in your notes and your homework. Okay, so those will be available unless they are the final answer. Okay, now, we are often asked to calculate the percent ionization, and that percent ionization is dependent on two things: the magnitude of the Ka or the Kb. So if you increase the Ka or the Kb, so the larger these values are, the more product you get. That means that you have an increased ionization, and we say that the acid or base is stronger. One is stronger relative to another. We'd be making comparative statements. So as you increase the Ka or Kb, you increase that percent ionization, but also that percent ionization is dependent on the molarity. Okay, so that's true as well. Now, this is the formula. You would take the H plus at equilibrium and divide it by the acid initially times 100 gives you your percent ionization of an acid. You take the hydroxide at equilibrium over your initial base, because this tells you what part of your whole was ionized or dissociated. Okay, so we're using ionization and dissociation interchangeably here. Now we're going to set up what's called a Rice table. So R stands for the reaction, I stands for initial, C is the change, and E is the equilibrium. Now what we did to compare, if we had that for stoichiometry, we had the reaction, we had the start, we had the shift, in which case it went 100%, and then we stopped. It was the end. It stops when the limiting runs out. I like to use different letters for this than Rice and make it clear that Rice is talking about an equilibrium situation. Okay, so we will plug in equilibrium values once we fill in that Rice grid, and we will calculate what we need for our final answer. Okay, so let's see an example. This shows you an example of cyanic acid. It's HCNO. That's not one you would have to memorize. The double arrow tells us equilibrium, and it dissociates to form an H plus and a CNO minus. Now, remember, H plus and H3O plus are the same species, okay, symbolically speaking. All right. Now, it gives us our 3.22% or 3.22 molar. That's our starting amount. Initially, I have none of either of my products. Now, when it was a stoichiometry, I would have lost 100% of my acid. So that would have been a minus 3.22. But this isn't 100%. It's much less than that, and I don't know how much I'm going to lose. Now, you could put an X here, But there's a reason I put an A, and I think that will become clear as we proceed with our example. Now, since this is a 1-to-1 mole ratio, I will gain A for each of these. Okay? So at the end, at the equilibrium, I have 3.22 minus A, I have A, and I have A. Okay, now what we then end up with is 3.22 minus A, and A. Now, since the percent ionization is very small, we can neglect that A. It'd be like neglecting 3.22 minus 0.0001, which is approximately 3.22. At our level, we're going to neglect this A because it keeps us from having to do the quadratic equation. Now, we set up our Ka expression. This is an acid, so everything's aqueous. Products over reactants. This is my formula, explicit, not just the word acid here, but explicit formula for my percent ionization. Now we can plug in. This you'll get from a table, unless it's your final unknown. In place of the H plus, I put A. In place of the CNO minus, I put A. So do you notice what I'm doing is I'm taking all those values from the E and I'm plugging them into the Ka expression. Now when I solve for A, I'm solving for H plus, A acid H plus, and I get 0.0241. And you notice then it's only one step to pH. That's why I like to use A and B. If you're solving for A, it's an acid, it's one step to pH. If you're solving B, it's a base, it's 2 steps to pH. Now, for the percent ionization, I take my H plus at equilibrium, which is what I just solved for, divide it by my initial times 100, and it's obviously far, far less than 100%. Okay, in the next couple videos, I'm going to do 2 of these for you. So until then, this is signing off.